everyone. Welcome to the next meeting organized jointly by quantum computing groups from Washington, D.C., from Harrisburg, and from Warsaw. And today, our guest speaker is Dr. Bettina Just, and she will give a lecture titled Explaining Circuit Model of Quantum Computing as if it occurred in an escape room game. So looks very interesting. And before we start, maybe I would just briefly announce that we have already scheduled a few more meetups. So the next will be on the 7th of August. And the title is Quantum Multibody Dynamics, Robotics and Autonomy. Then we'll have 3 meetings in September. So the first will be on 11th September, Quantum Computing for Quantum Chemistry, later Quantum Machine Learning Lightning Talk, and finally Quantum Communication on September 25. So we would also like to thank our sponsors or partners who helped us organize this event. So Quantum AI Foundation and Warsaw Quantum Computing Meetup, Harrisburg Quantum Computing Meetup, Alexandria Quantum Computing Meetup, Quantum Computing and Data Science Group from Toronto, Brooklyn Quantum Computing Meetup, and Orion X Net and Association Quantum. This is final slide. So I think we can start. So Bettina, thank you very much for accepting our invitation. It's our pleasure to have you here. And the talk looks exciting. So let's start, and the Zoom is yours.
Thank you. So I'll share my screen. Okay, this is the title of the talk. Thank you for the very nice introduction, and thank you for the invitation. I already was invited once, but I thought, well, it's so trivial what I'm a mathematician. What I'm presenting, I do not know whether it's okay to present it here. Okay, so let's see whether it's okay. Explaining circuit model of quantum computing as if it occurred in an escape room game. Just a few words to who am I. I got a PhD in mathematics and computer science from the Goethe University at Frankfurt some decades ago in the last 1,000 years. And then I went to industry, to assurance companies. And since 2010, I am a professor at the THM, which is a University of Applied Science in Mittelhessen, Mittelhasia, in Gießen, in the middle of Germany. And I am also a co-founder and coordinator of a network. It's called Quanten an HAWen. It's Quanten at Universities of Applied Sciences. And the content of this talk was first published in a book which appeared at Springer at the end of the last year. It's called Quantum Computing Compact, and then it's German, Spukhafte Fernwirkung and Teleportation endlich verständlich. But it will be translated to English and it will appear in English at the beginning of the next year. Springer is going to translate it. If you want, well, we see, if you want some documents, so let's talk about this. Okay, the topic of this talk is teaching. So I will not present any new scientific results or some new applications of quantum, but it's on teaching quantum computing to explain things. And this is the homepage of the German government of quantum technologies. And there are 5 areas: quantum computer and simulation, quantum communication, I think it can be read good, also it's German, measuring with quantums, basic technologies, and outreach. Outreach is teaching in academia, but in research, but also teaching to the public, to schools, to smaller companies who maybe want to enter the subject and do not know how. And this is our main area, to teaching quantum to students who are not specialized in mathematics or in computer science or in physics, but they have kind of basic knowledge, and so the things have to be explained easily. without much formalism and so on. So what was the idea? And I'm curious whether you know the situation. My original problem was teaching teleportation. Okay, teleportation is not a very difficult circuit, quantum circuit. This is the circuit of teleportation. I think you know it, and if you don't know it, doesn't matter. It's a very small quantum circuit. And I thought about presenting this, and of course, a mathematician has to prove why it is correct. So it is easy to see why it is correct. This is why it is correct. Okay. Yeah, this was why it is correct. And my situation was, I can follow step by step. Yes, this, and then here, and then here. Okay, everything's fine. But I have no idea what is happening. I have not the slightest idea what is happening. I would never have been able to find such an algorithm, a circuit on my own, because I do not get the soul of the algorithm. I only see it can be calculated step by step. And I couldn't sleep about that. It was horrible because no idea. And if one looks at unitary matrices, the same effect occurs. I can multiply unitary matrices and everything turns out fine, but still no idea. So the question was, how can it be visualized? There must be some idea. And I confess, I played some escape room games at this time. And here are some typical things, maybe you know them, that in this way or slightly in this way can also occur in escape room games. So here one has to arrange the numbers, and here one has to free this thing, and this is Rubik's Cube. One has to move and shuffle and to get a solution. So I thought to myself, maybe something like this can help to visualize teleportation and quantum circuits. And it turned out that it worked. Otherwise, I would not be here today. So now the topic of this talk is, how can it be visualized? Let's look at a register of 3 quantum bits, and mostly we will talk about a register of 3 quantum bits in this talk. And for the moment, we do not look at gates yet, but we simply look at the state of the register. As I think you all know, the state of a register of 3 quantum bits has this form. It is given by 8 numbers, the so-called amplitudes, which when squared and summed up add to 1. And these numbers can become, usually are complex, but for teleportation, explaining teleportations, one can also think about real numbers. It makes things easier. So these 8 numbers are called alpha 0 to alpha 7, and they add up to 1. And here's an example with real amplitudes. So they are all squared, and when they are all roots, so when squared, you see that those guys add up to 1. These are the amplitudes. And now the idea is to, usually the state of a register is represented as a vector in 8-dimensional space. And 8-dimensional space for most persons is a thing which cannot be visualized very good. So my idea was to think of the 8 edges of a cube, or the 8 edges, vertices of a cube. If one has a normal cube, so this is a normal cube, and this guy has 8 vertices, and everybody knows that. So the idea was to somehow put these amplitudes to the edges, to the vertices of a cube. To the vertices. It's terrible. Okay, to the 8 vertices of a cube. Let's see how it works. So here are the vertices of the cube. And we imagine this cube to be located in a three-dimensional Cartesian coordinate system. So the first qubit is responsible for the left and right direction. If it's 0, then we are on the left. You see here the state is 0, 0, 0, 0. Of the first qubit, left-right direction, and if it's 1, then we are here on the right side. These are the usual Cartesian coordinates. And this idea may remain in your mind. The first qubit is responsible for left and right, and the second qubit is responsible for down and up. If it's 0, then we are down. Second qubit 0, 0, 0, 0. If it's 1, we are up. Yeah? And the third qubit is responsible for front and back. In the front, it's 0, the third, and in back, it's 1. And now the idea is to place these amplitudes with their states. So alpha 0, the amplitude of the state 0, 0, 0, will be placed here. And alpha 1, the amplitude of the state 0, 0, 1, 0, 0, 1 is here, will be placed here. And so on. So at the end, alpha 7 is the amplitude of the state 1, 1, 1. It will be placed here. Let's look at an example. Here is an example, the example we looked at. And we have real amplitudes. Green means positive amplitude, red means negative amplitudes. And okay, this is square root of 2 over 16. It's placed here. No, no. It's placed here, exactly. It's placed here. And you see, this is a small little square, and it has the area of 2 over 16. Thus, it has the side length of the amplitude, square root of 2 over 16. And the next one, 0 over 16, is placed here, and so on. 3 over 16 is the length of this guy. And here we have a red one, because this is negative amplitude, and the amplitude is square root of 1 over 16, though the area is 1 over 16. Okay, it's from an information theoretical point of view, nothing happened. It's exactly the same information, whether we have these 8 numbers here or whether we have these tiny little squares at the vertices of a cube. It's the same information. But it turns out that algorithms can be visualized with this model. Okay. Questions so far, or everything okay? Everything fine?
There are no questions, so I think we can go on.
Okay, n equals 3 is, to my opinion, is a very good example, because for n equals 3 qubits, one has 2 to the n. This is 8 states, and nobody has the idea of separating these 8 states to the 3 qubits. It simply doesn't work. N equals 2 is because 2 pi 2 is 2, 2, the 2 is more difficult. But let's look at other numbers of qubits. So if we have only a register of only 1 qubit, then it can be represented like this. Real amplitudes, green positive, red negative, and so this is a visualization of a state of one qubit. Here's an example. N equals 2. Okay, n equals 2. We have a 2-dimensional cube, which is a square. And here we have an entangled state. The entangled state 1 over square root of 2 times 0, 0 plus 1, 1 means that the probability weight is distributed in a fair way between 0, 0 and 1, 1. And this is the graphical representation of this entangled state. A not entangled state would have tiny little green squared at any of the corners. N equals 3. Okay, here's a we already talked about this, and it can be extended to n equals 4. In this case, we would have an inner and an outer cube. Okay, this was the first remark. Second remark, of course, you are asking, and what about complex amplitudes? Complex amplitudes work as well. And this is, I'm following an idea of Richard Feynman in his quantum electrodynamics. This is a page from his book where he presented these tiny little squares and amplitudes. So if we are talking about complex amplitudes, it's not more necessary to talk about green and red, but we just have one color, blue. And an amplitude is represented by an arrow which is in the complex plane. So this would be I2. And this would be, here's always the origin, and this would be some minus I, minus 1, minus I, something like that. And the square is always on the left side of the arrow. So this is the way to represent graphically complex amplitudes. And it works. But for this talk, I'll not go to very great detail for that. Okay, now that we say we placed our amplitudes on the, let's remain at the three-dimensional cube, then we ask what means measuring. Measuring mathematically is a projection and it's a formalism, but one can also think about measuring is removing uncertainty. So if I'm measuring the first quantum bit, then I'm no more unsecure about the first quantum bit. It's either 0 and then I am in this world, or it's 1 and then the measurer we are in this world. And graphically, it's like cutting the edges in left-right direction of this cube. Remember, the first quantum bit was responsible for left and right. So measuring it will remove all the left and right edges. And what remains are two-dimensional cubes, squares. Then, of course, the amplitude have to be blown up so that the sum of the areas of the squares is 1. But the relation between them stays as it is. We have here a tiny little green and 2 tiny little red ones, and so we have here green and 2 red ones. This is the way one can illustrate measurement. So imagine we are measuring the first qubit and then we are measuring the third qubit. The third qubit is responsible for front and back. So measuring the third qubit will remove all the edges between front and back. See? This is what measuring the first qubit does. And then this here, just like cutting the edges, is what the third, measuring the third qubit does. So what remains is one of 4 worlds, because the results are 0, 0, 0, 1, 1, 0, or 1, 1. And it remains only the uncertainty of the second qubit, up, down. This is the illustration of measurement. Oh, fine. If there are no questions, then I go to what gates are doing. But if there are questions,
actually, there's one question on our chat. There is a question: what happens if n is equal to 5?
it gets,
We should think in 5-dimensional.
we should think in 5 dimensions, yes. Of course, illustrating it becomes difficult. Maybe at, yeah, with 5, maybe it's still possible, but at 6, I'd say this is the end of the model. And the model serves to get a feeling for what is happening with these quantum algorithms. I think it's a little bit like geometry. If one is, one can have a feeling of geometry in dimension 2 and 3 and maybe 4, but geometry also is done in higher dimensions. And it's good to have a feeling for the lower dimensions.
Okay, there's one more question actually.
Yeah.
So Barry asked, so am I right is understanding that qubits that have been measured are not represented on the diagram?
Yeah.
So after doing measurement, yes, we don't consider, so yeah, so we reduce the dimension, right?
Exactly. For instance, if we are in this first image, we measure the first qubit and it turns out, let's say the first qubit is 0. Then we have, okay, we have the states 0. They all begin with 0 because the first qubit is 0. So we can also think about omitting in this resulting world, omitting the first 0, and what remains is 0, 0, 0, 1, 1, 0, and 1, 1 for the second and the third qubit. They can be removed, then they are redundant. Then this 0 in the first qubit is redundant, it can be removed.
Okay, we can go on.
Okay. So let's look at the interesting thing, and these are the gates. The gates, what are the gates doing? So let's look first on Pauli X gate. Pauli X on 1 qubit, as you know, applied to a state alpha 0 times 1 plus alpha 1 times, alpha 0 times 0 state plus alpha 1 times 1 state. It will interchange the amplitudes of the 2 states. So graphically, it means, okay, we have here state, tiny little red, slightly more green, and applying Pauli X will interchange the 2 squares. Okay, now what happens if we apply Pauli X to, let's say, the first qubit, but in a register of 2 qubits? So we apply Pauli X on the first, which means the left, right. The first qubits is always responsible for left and right. Left and right. So we interchange the along the 2 left and left-right edges. This is what happens when we apply Pauli X to the first qubits. We interchange everything along the left and right edges. So we have here, this goes here and this goes here. See, green is now here, the red is one here. And these 2 are interchanged. The big one goes here, the small one goes there. That's what happens. What's Pauli X doing? Okay, and now you can imagine what happens when Pauli X is applied to the first qubit in a register of 3 qubits. Okay, now, the example is to the front back qubit. Okay, it's more challenging. What happens? Please imagine a little bit. We are applying Pauli X on the third qubit in a register of 3 qubits. Third qubit is responsible for the front and back direction. So we will interchange everything here along these front and back vertices, the 4 front and back vertices. Okay, that's what we do. These 2 are interchanged. Red goes in front, green goes back. Here nothing happened because there was nothing. here the red one came in front, and the nothing went back. And here vice versa. The red goes back and nothing comes in front.
It looks that we have one question regarding this slide. Why 0, 1 is not on the left side of 0, 0 in the square? So I guess that in the square, so probably this is the second level when we apply x on first qubit. And the question is why 0, 1 is not on the left side of 0, 0.
Yeah, this is okay. Usually it's reverse order. If you are used to this way to writing I to represent the binary representation of the number I, for instance, I think the question is on the order of the qubits. In my presentation, the first qubit is the one that is here, 1, 0. The 1 is the first and the 0 is the second qubit. I know that in literature it's quite, usually in advanced literature, it's in the opposite way. And in beginning, it's that way, because it's more easy to say the first qubit is in the first position.
Okay, I hope that it answers the question, but I'm not sure. If not, then please, it was asked by Team Orion X. So if you still need clarification, then please just ask next question.
Yes.
But as for now, I think that we can go on.
Yeah, just a second. I found the chat and I'm very glad about that.
All right. Okay.
Okay. Next. No. Okay. I just rearrange my.
Okay. Good.
Okay.
In the meanwhile,
now let's.
I see now in computer science it's. Okay, it's 0, 0, 0, 1, 1, 0, 1, 1, but now it is 0, 0, 1, 0, 0, 1, 1, 1. So I think that it's clear now. Okay, thank you.
Okay.
Thanks.
Next gate we are looking at is Pauli Z. Pauli Z gate. Pauli Z, as you all know, is changing the sign of the amplitude of the state 1. So alpha 0 times 0 plus alpha 1 times 1 goes to alpha 0. This is a typo. Alpha 0 times this should be a 0 minus alpha 1 times 1. So this state, red and green, goes to the red one stays, and this guy at the state 1 changes its color. This is Pauli Z on 1 qubit. And now the same effect comes. Let's apply Pauli Z to the first qubit in a register of 2 qubits. So everything will happen along these 2 edges, which means that that guy and that guy will change their color. See, that's what Pauli Z applied to the first qubit in a register of 2 qubit does. It's applied on this side, change the color. And now rethinking about applying Pauli Z to, as before with Pauli X, to the third qubit, front back qubit, in a register of 3 qubits. The third means we are dealing with all the edges that go from front to back. Set on the third front back qubit in a register of 3 qubits. To those edges we apply Pauli Z. And the effect will be that any amplitude which is on the back side of the cube will change its color. And that's what's happening. These 2 remain as they are. And these 2 change their color. And this sounds like escape room game, shaking the dice and changing the color. Okay, let's look at a little bit for who is interested in complex amplitudes. Let's look at, it's only a remark, if you are not interested in complex, doesn't matter, but just to see the phase shift. It's a general Pauli Z is the phase shift. So here it's applied on 1 qubit. It will change this phase. Applying it to the first qubit in a register of 2 qubits, one sees that these two are turned around. These two states are turned around. The 0 states remain as they are, where the first qubit is 0 remain as they are, and these will be turned around and applied to the first. This is now the first qubit in a register of 3 qubit. Leads to the fact that all these squares, which are on where the first qubit is 1, all these squares are moved by the same angel, by the phase. So that's how it looks with complex gates. Okay, more gates. Very famous quantum gate, of course, is the Hadamard gate. Let's look at Hadamard, what it does. You know what it does. Hadamard applied on 1 qubit and on a 0 state will not turn around anything, but it will divide the area and place half of the area on the 0 state and half of the area of the on the 1 state. So that's what it does, Hadamard. Hadamard applied on the 1 state also will divide the area to two equal sized squares, but this here gets red. And Hadamard applied on an arbitrary state like this here is doing the same thing. So it does to this red one what is done on the 0 state, and it does to the green one what is done on the 1 state. And then this is completely, this is not right. This should not be complete. This is almost completely red. Don't know whether you see it. It's almost completely red and very little green here. And I think this is exactly the art that one learns when one is playing these kind of computer games. One gets a feeling to mixing up everything.
Okay. So there is a question on our chat regarding slide number 14, so the previous one.
Okay. So so I suggest to finish Hadamard and then go back to the previous.
Yes, this is fine. Mm-hmm.
No, to finish Hadamard, genau. This is Hadamard on the 3rd qubit in a register of 3 qubits. And it's always the same effect. If we are applying a 1 qubit gate to 1 qubit in a register, it means that things happen along these edges of the cube that point in the direction where this qubit is responsible. So Hadamard on the front, on the 3rd qubit, front, back qubit means that things are distributed along these 4 edges. You see this red one is distributed. Here, the 3rd qubit was 1, so it changes color. And this green one is distributed here. And this red one is distributed here, and this green one here. That's what Hadamard is doing. It's shaking around. Okay, so I go back to the slide with shift. And what was the question?
Yes, so the questions, yes, you can read it, of course. Would they, if not move by the same angle? And is the phase shift the same for all the change?
Yes.
For all that change. Mm-hmm.
Yes. They all move by the same angle. Yeah, so here we have a phase shift of, well, I would say it's about 20 degrees counterclockwise. And also here we have a phase shift of 20 degrees counterclockwise. So this tiny little angel moves 20 degrees counterclockwise. Yeah, now it's here, 20 degrees away. And also this one moves 20 degrees counterclockwise. So it goes here. It's no more like that, but it's now moved 20 degrees counterclockwise. And here it's the same. Everything is moving 20 degrees counterclockwise. Everything on this, on the right face of the cube.
Mm-hmm. Okay. I think there is another question. Please, could you give some idea in terms of visualization? We have a particle, whether trapped ion, electron cloud, or anything, they are in a superposition. When we say amplitude, I'm assuming it's crossing. I'm not sure if I understand this question, but
no, it's I also do not understand the question, because this is on logical qubits. So a physical qubit is for example trapped ions, but this here is a logical qubit. It's an object that has a state, and the state is alpha 0 times 0 plus alpha 1 times 1.
Okay, so maybe the person that who asked the question can maybe try to rephrase it and maybe ask it again, or maybe the answer that Bettina has given is.
Could I try by the voice, please?
Yes, go on.
Thank you. So I understand these are logical qubits. Essentially, what I'm trying to understand is you look at any particle. It could be anything, literally. You know, let's say electron cloud or whatever. Yes. And they're in a superposition, right? And yes. these gates, what we're discussing right now, they're essentially describing the amplitude of that electron cloud, for example. So from a certain threshold, which we describe as finally when we measure it, is going to be either 1 or 0 in a very simple nutshell, right? Whether it's 0, 0, 1, or eventually is going to have a proper amplitude when it crosses a certain threshold. Now, in terms of looking at this waveform, let's say, for example, Hadamard gate, where you take anything and it puts it back into a superposition. You know, you take some qubit, it puts it back in superposition. So what are we actually saying when we are saying something like this? We are reconverting that amplitude back to something that's not, because waveform is still there. I'm just trying to visualize, connect the logical with the physical in terms of visualization. You see what I'm saying? Yeah,
I think, yeah. And what we are doing is we have, let's say we have one qubit here, and it is in superposition, and the state of the qubit is visual in its superposition. It's visualized by these tiny little squares. And then we are applying a gate on this qubit. And applying the gate is visualized by, depending on the gate, for instance, by.
So for example, if we apply, for example, let's say we apply a Hadamard gate on one thing. So essentially we're doing it, we're perhaps increasing some magnetic field or something to bring it back into this, you know, something like that, just to, But how does these two actually connect? Because this visualization, we are already assuming that it is in that amplitude. How does it go back? I don't know if I'm able to, it's very difficult for me to explain this, but I think you're getting it, maybe.
Yeah, I think the question is on physics, what you're asking. So Hadamard is a gate if the qubit is in an unentangled state, it's in a pure state 0, then applying Hadamard will give us this. If it's in the pure state 1, Hadamard will give us this. And if it's in a superposition state, then the result will be another superposition state, which is formed by certain rules. I don't know how, so I don't care about in this talk how it's done physically. It's the gate model of computation.
Understood. Thank you so much. Maybe I'll reach out. Very kind. Thank you. I think that was a great
I hope,
explanation. Thank you.
yeah,
No,
maybe,
thank you.
maybe later
Absolutely
on.
fine.
Okay. So this was Hadamard, and now let's continue with Hadamard mixes amplitudes. That was your question. So now let's look at the C0 gate. C0 gate is, as you know, is a gate which is applied on 2 qubits. One, and here it's the first is a control qubit, and the second, the down-up qubit, is a target bit. So applying C0 can be visualized. Remember, the talk is only on visualizing things. It can be also computed with unitary matrices, but this is visualizing what C0 does. C0 with the first qubit or as control bit will operate where the control bit is 1. So it will operate here or here. And it will manipulate the second qubit, which is the target bit, and it will interchange these 2 amplitudes. This is an example. These 2 remain as they are, and this goes up and that goes down. Now applying C0 to a register with 3 qubits. Here's an example. We have a register of 3 qubits, and now we apply C0. C0 on what? C0 with the second qubit as control bit. The down up is controlling. So where the down up is up, yeah, something is happening. And the first qubit is a target bit. So the first qubit will interchange its amplitude where the second qubit is 1. And this is what's happening, applying C0 on a register of 3 qubits. The third qubit is not involved in this C0, but it's of course in the register. So also the states with the third qubit are changing. And this is what's happening. These 2 interchange. These 2 interchange. And these down, where the control bit is 0, remain as they are. Okay. It's only visualizing what's happening. And if it's not necessary that you go to all details, but just keep in mind that C0 does somehow mix and interchange. So Hadamard is mixing, and C0 is interchanging, and Pauli X is interchanging, and Pauli Z is changing color. Now let's look the teleportation algorithm. The original idea was to visualize the algorithm. So what is the situation with teleportation? Alice and Bob are far apart physically, but each of them has one of a pair of entangled qubits, and Alice has a third qubit. This is the start situation. Here's this third qubit. It plays the role of the third qubit, so we visualize it by front and back. And the first qubit is with Alice, and the second qubit is with Bob, and these 2 are entangled in this entangled state, entangled state. So this is the start situation, and written as one, this is the start situation. And what they intend to do, they want to give the state of that third qubit, so this front-back state, they want to give to Bob's qubit. But Bob's qubit is the down and up qubit. So they somehow want to transport this situation to the up and down state. Okay, as one register, written as one register, the situation is a 3-dimensional cube, a register of 3 qubits, and the third qubit goes here and here, where Bob's and Alice's states have non-zero amplitudes. So you see here in this register, you see the third qubit, you see it twice. Tiny little green, big red, tiny little green, big red. And it's with the states 1, 1 and 0, 0 of the first 2 qubits. And now what does the teleportation algorithm do? This is the circuit, and what is happening? We start with this 3-dimensional state, Now Alice applies C naught on her qubit and control bit is the third qubit. Graphically means the C naught is applied on the back side in the direction of the first qubit. It means that this red will go here, this empty will go here, and this red will go here, and this empty will go here. If you do not follow the details, doesn't matter, just keep in mind we are in this situation. We have the information of the third qubit in the direction of the third qubit. Here it is, here it is. And now we are applying C naught, and C naught interchanges. So we arrive in this position, in this situation. Then we apply Hadamard. And Hadamard on the third qubit, here it is, Hadamard on the third qubit distributes the states, distributes the amplitudes along that qubit. So here's distributed. This was here and here was nothing, though here's now a green and a red, and here's distributed. And here's distributed. And here's distributed. And then, having done this, then Alice measures the first and the third qubit. Measurement, we recall, is we have only the columns remaining. And these columns are tiny little green, red one, tiny little green, red one, blown up so that the sum of the areas of the squares is 1. Tiny little green, big green, yeah, tiny little green, big green, tiny little red, big red, tiny green here, and big green, tiny green. So this is the situation of Bob's qubit when Alice is measuring. And now we see that the information almost is at the top down columns, which means at Bob's qubit. This is the situation of Bob's qubit, and Bob does not know anything. Bob has not measured his qubit. He only has the qubit, but he does not know anything of the state. And now Alice is phoning him and says, hey, Bob, you are in that column, or in that column, or in that column, or in that column. So what Bob has to do, well, if he knows he is in that column, he already has the situation of the third qubit. Remember, the third qubit has tiny little green and big red, tiny little green, big red, it's already there. Or if he is in that column, then he has to change the color, Pauli Z, apply Pauli Z, changes the color. Or if he is in this column, then he has to interchange the both amplitudes, Pauli X, interchange. And if he is in this column, he has to interchange and then change the color of the bus. That is Pauli X and then Pauli Z. And then his bit is in the situation it should be. Recall the state situation, it was like that, and the third qubit in front and back direction now is in up and down direction. Okay, it works. It's visualizing teleportation. And now I can imagine, okay, knowing what one can shake and dice, and one can have such an idea. Let me briefly look at other algorithms. Deutsch-Joscha algorithm, maybe you know, the problem is we have a function of one input and one output, and we have an oracle, and we want to know whether this function is balanced. That means has 1 0 and 1 1 in output. So if it's one of these two, or whether it's constant. And we have to decide whether it's constant or balanced, and calling the oracle only one time. This is also, classically it's impossible. And here's the quantum circuit. Okay, this is also such a quantum circuit where I would say, I do not see anything. I can follow it step by step, but why does it work? Okay, it works like this. This is, the the background is now black because it's coming out of a program. Okay. This is a starting situation. Then Deutsch Joshua is applying Hadamard, distributes, reapplies Hadamard, distributes everything. And then the oracle exchanges the down-up amplitudes if and only if the value of the function is 1. So if f is the 0 function, then there's not interchanged nothing. It remains as it is. If f is the 1 function, is interchanged everything. If f is the identity, then these two are interchanged. And if f is the not, then these two are interchanged. Okay, so this is the situation after the oracle. Then Hadamard is applied, then Hadamard is applied again. And then one measures the first qubit, and we see, without going to details, we see measuring the first qubits means cutting along these edges. So if the function was 0 or 1, then the weight is, the first qubit will be 0, all the weight is here. And if the function was balanced, then all the weight is here. The first qubit will be 1. Okay, so it works also, management summary, it works also for illustrating Deutsch Joshua algorithm. Okay. I can't hear the audio anymore for the game. Yeah, now I see that there is a question. Can it formulate it mathematically? Of course we can. What I'm presenting is a group of movements, and this group is generated by certain movements, and the group operates on the edges of on the weights on the edges of the dice, and it's generated by these operations which represent the gates. And what we usually see in quantum mechanics is the representation of that group by unitary matrices. And representation of the group always has the advantage that one can calculate easy with it, because we are dealing with matrices, and matrices are very fine to calculate. But matrices are not so easily to visualize. So this is the mathematical formulation. I'm talking about a group which is represented by quantum mechanics. If you want to, you can download it from my homepage. Here is an URL. We have made a program. It's called Curacle. It's still very beta, but it works. And work is ongoing. The next steps are to visualize other algorithms. For instance, Groover search. I think with 4 qubit it should work, and to extend everything to complex gate. This is quantum Fourier transformation. Very nice, very nice. All the weights are distributed and turned around by, you see here, turned around by every angel in 90 or 45 degrees here. Everything here. Lot of bits reversed. Okay, I know that. Okay, summary. So main ideas. The takeaway home message is visual teleportation can be visualized in this way. One can follow these weights, and that's what the mathematical proof does. But here it can be seen, it works. And for me, it could be an escape room game. Shake the cube so that these tiny little squares arrive in the right positions and before measuring. And higher levels would be mixing and rotating squares with complex amplitudes. And there in comes an intermediary step for the addition of complex arrows. One can imagine, for instance, the root of naught or this RXX gate for quantum annealing. Okay, this is the book, and I'm at the end of my talk. I thank you for the questions and for the attention. And if you want to contact me, here are my contacts. But this is the summary. So thanks a lot.
Great, fantastic. Thank you, Bettina, for a very interesting and inspiring talk.
Thanks.
So I can see that our participants enjoy it. So do we have any more questions? I think that
Yeah, there is.
go on.
And the question is the first part of my comment on the chat, because you answered it in the context of your talk, but you motivated things first by the games, and I'm fascinated by games, and the feel that good players cultivate for a game, also in sport, is, here is a question: can that feel be formulated mathematically? And also, what's the role of that feel in designing quantum computers, circuits, and so on? So there are two parts here.
Well, I did not present anything which is new in respect to quantum gates or quantum algorithms. Everything is known. And it's only visualizing these things. And I think when one starts with quantum algorithms, it's nice, or one should get a feeling for this algorithm. Like if you ever studied Turing machines, one usually starts with deciding whether the numbers of zeros is even or odd, and then somehow one gets a feeling for Turing machines. And here, at least to me, it was, I did not get any feeling for quantum algorithms. And now I get, playing around with it like that, I get a feeling for quantum algorithms. So I can also talk about quantum algorithms in higher dimensions because I have this basic feeling now. And I could imagine in an escape room game to transport this feeling in the sense of, well, you have this cube and you have these weights, and your task is to shuffle it around and play with it so that the following situation is there at the end. And the game does not already exist. We have a program and we are working on this program, but it's not yet a computer game. It would be, if it was a computer game, it would be one that that is fun and transports a feeling for quantum algorithms.
That's a great question, answer. Thank you.
All right. Do we have any more questions?
Thank you. Okay.
Okay, I got some more questions on our chat. There was just one question a bit earlier. I'm not sure if it has been already answered. Is it possible to have an English version of your paper in your site?
Yeah. I was asked this in the German meetup, and I thought what to do. And I have a lecture. I have a PDF lecture, and this lecture is translated to English. So it's quite a big PDF, but there's everything in. Is there a possibility? So I could send you this send this PDF somehow. For me, it would be okay so if it's distributed.
Yes. So you can send it to us, especially to Helen and the Deb, and I believe that they will be able to just distribute it to all the registered participants, I guess. Is this correct, Helen? Or Deb? I think they should be able to do it. So there's actually one more question on our chat. What do you think are the limitations of a quantum circuit?
I think
it's more general question, I would say.
Theoretically, there are almost no limitations. The question with quantum computing is, of course, the hardware, but theoretically, I don't see
Yeah.
I don't see limitations on quantum circuits. It's yeah. Maybe I do not understand the question right. Is
Yeah.
it on what problems can be solved by quantum computers?
Yeah, Tushar, so maybe you can try to clarify a bit, or maybe Bettina has already answered your question.
Yeah. So as we know, like in the electronics, like in analog circuits and digital circuits, we say like analog circuits are more prone to noise and all those. So we developed like digital circuits to come across that. So like anything like similar, like do we have in quantum circuits, like, or they are like, they don't have anything, something like that will limit them in future.
I'm afraid I did not understand. For
Yeah,
acoustic
yeah,
reasons or for the
yeah.
language reason, can anyone? I did not get the question.
Okay, yeah. Let me rephrase my question again. So what I'm trying to say, like by limitation, I mean like as we currently we are seeing like quantum circuits, we can do a lot of things. I mean, we can imagine unimaginable things right now. But do you think at some point in future there might be a situation where we'll say like, oh, I mean, this is the thing. This is the thing can't be done by a quantum circuit.
Well, I think undecidable problems like the halting problem will not be decidable by quantum computers, or not.
Yeah, so this is at least
maybe I have a problem with if you ask me what are the limitations of a Turing machine, I don't know the answer. Quantum circuits theoretically can be arbitrarily large, and
yeah. But
and
I think, Bettina, that your answer is very good, right? So, for example, quantum computers probably will not solve some undecidable problems like this halting problem, right?
no, yes, no, they will not.
Yes. So this is one of the problems that will not be solved by quantum computers. So I'm not sure, Tushar, if it answers your question, but this is the same in case of Turing machines, right?
Yeah. I got it. Yeah. Got it. Yeah.
Okay.
Thanks. Yeah.
But of course, also as Bettina said at the beginning of answering this question, so beside these theoretical limitations, of course there are still limitations from a physical perspective, right? So we still are not able to build arbitrarily large quantum computers with many more qubits and perfect fidelity, let's say.
Right. Yeah.
So, mm-hmm.
Yep. Thanks.
Okay, thank you.
I see.
All right. There is also an answer from Bruno. You can do all that is unitary with a universal set of gates. Yes, so this is also true.
That's
okay.
True.
But all right. So currently I don't see more questions on our chat. So I think we can conclude this meeting. There are some very positive comments that it was a great meetup, very clear explanation. So I can agree.
Thanks.
Yeah. So I think that we don't have more questions now. Oh, there's one more question actually. Can the qubits currently allow factorial calculations via these methods?
I don't know yet, because it's one needs too much qubits for Shor's algorithm. I think you're talking about Shor's algorithm, and it
yes,
takes
I think so. That
much
is a question about factorization.
We are in 8-dimensional space, at least. Yeah.
So currently, as far as I'm aware, we can just factorize relatively small numbers still. So so you can sleep well. Your bank account is still safe with contemporary quantum computers. At least the computers that are still that are publicly available, because maybe there are some secret services that possess much more powerful quantum computers than the devices that we know and we heard about at least, but who knows? Safe for how long? It's also hard to say. I think that we are not able to predict the future of quantum computing right now.
No.
So of course there are some ambitious plans of several companies and estimations that will have much more powerful quantum computers within 10 years, but there were similar promises in case of autonomous vehicles about 10 years ago, and currently I think that we are still many years behind the things that were promised about 10 years ago. So probably we should be careful with with any predictions and estimations.
That's good. It gives us time to learn more and understand it better.
Yes,
Yeah.
that's correct.
I'm okay with it taking a little while.
Yes. So anyway, this is a perfect time for doing research in this area. This is for sure. So for learning more, for doing research, this is a perfect time. It's not necessarily a perfect time for doing business or thinking about some real world applications, I guess, but who knows? It's possible that there might be some huge advancements in the coming years or maybe even months that will be announced soon. So we should be prepared for sure.
Well, if you
So
want to, if you want to be able to predict the future, be part of creating the future. That's
yes.
Bill Gates' mantra.
Yeah. So I heard that it was even attributed to Abraham Lincoln, in fact, that the best way to predict the future is to create it.
Abraham Lincoln, Bill Gates, they're the same.
Yeah, close enough.
Close enough.
Yes. There's a question: what's the current number of factorization known with and with how many qubits?
I think with the circuit model, it's still 15 and 21, something like that.
Something like this, I guess.
With quantum annealing circuits, this D-wave model, there have been factored numbers with 6 decimal digits. So
I'm not sure. So
it's a completely different approach, of course, but it works better. Still, it's nothing which my handy cannot do. Factoring a number below of 1 million is not so difficult, but still it's not absolutely trivial.
Okay. Yeah. So regarding these questions, whether we are safe and for how long we will be safe, I think that it's also good to know and to be aware of research on quantum cryptography, because there are already some quantum communication protocols that has been proven to be safe even in the era of quantum computers, factorizing large numbers. So as far as I know, it has been proven that will not be able to just crack such quantum cryptography protocols using any currently known physical or mathematical methods. But anyway, in such a case, we'll have to just replace our cryptography methods that we use nowadays. But I heard that there are already experiments, at least, showing how we can do it. So there is a hope.
Have a good weekend, everybody. Thank you, Bettina.
Thank you. Thank you very much.
Good appetite, good lunch. Bye. Thank you.
Bye-bye, and we hope to see you next time on 7th of August.
Yeah, I'm a fan of Quantum Meetup. Also, it's sometimes hard at midnight in Germany, but I'll do my best. Bye.
Perfect. Bye-bye.